Imagine a world where the sky is not blue, but a dense orange haze heavy enough to let you fly with wings strapped to your arms. A world with methane rivers that cut through alien sand dunes, and opaque clouds that change with seasons lasting decades. What if I told you this world, Saturn's largest moon Titan, is hiding a bizarre atmospheric secret that could upend our understanding of planetary science, and maybe even decide the fate of NASA's next great mission? Just recently, scientists poured through data from the legendary Cassini-Huygens mission and spotted something no one was expecting. Titan's entire atmosphere appears to wobble like a gyroscope, moving separately from the moon's own rotation. This isn't just a quirky detail in an alien world, it's a stubborn puzzle, one that might rewrite what we think we know about weather, climate, and even the very ingredients for life. Why is Titan's atmosphere behaving as if it's disconnected from its surface? And what invisible hand is twisting it out of alignment? The answers could define the future of robotic exploration, and maybe a lot more. Let's zoom out for a second. Titan is no ordinary moon. Discovered in 1944, it's bigger than Mercury and shrouded in an atmosphere so thick the surface pressure is 50% higher than Earth's. The air there is mostly nitrogen, but it's laced with methane, forming clouds and, incredibly, producing rain that fills lakes and rivers with liquid hydrocarbons. Picture standing on a surface of icy rocks beneath a sky where it rains liquid methane, and the dunes around you are made not of silica sand, but of organic compounds. In 2005, the Huygens probe became the first, and still only, spacecraft to land on Titan, surviving a descent through those dense clouds. The images it sent home showed drainage channels, pebbles rounded by alien rivers, and a surface that feels both familiar and utterly surreal. The Cassini orbiter, which relayed Huygens data, spent over a decade mapping Titan's surface and atmosphere. Those years transformed what we knew, revealing methane lakes and even hints of ice volcanoes, called cryovolcanoes, that could be spewing ammonia and water from a hidden ocean below. As Cassini's sensors peered through the gloom, scientists steadily built a profile of Titan's climate. Wind-blown hydrocarbon dunes stretching for hundreds of kilometers, storms rolling through the haze, and cloud patterns shifting with the changing seasons. But it was the atmosphere itself that kept giving up surprises. Titan's air is not just thick, it's dynamic. Seasonal changes unfold slowly, since a Titan year is nearly 30 Earth years long. As spring and autumn trade places, clouds gather and recede, immune to the sun's feeble rays at Saturn's distance, yet energized by mysterious internal dynamics. Then, hidden in the mountain of mission data, came a shock. When University of Bristol scientists compared the temperature fields of Titan's surface and atmosphere, they noticed the atmosphere wasn't lined up where it should be. Instead, it seemed to tilt, the entire gas envelope lurching off the pole by several degrees. Stranger still, that tilt changed with the seasons, as if the atmosphere was performing a slow, stately dance. This was more than a weather anomaly. The whole atmosphere was in sync with the season, yet strangely unmoored from Titan's solid surface. Lucy Wright, the study's lead author, summed it up. Titan's atmosphere behaves like a gyroscope, stabilizing itself in space, suggesting a past event disrupted its spin. Her team watched, perplexed, as the tilt's direction remained fixed in space, not following the sun, not tugged by Saturn, but apparently set by some unknown force. What's puzzling is how the tilt direction remains fixed in space, rather than being influenced by the sun or Saturn, added Professor Nick Teenby. Instead, we've got a new mystery on our hands. This atmospheric gyroscope isn't just a scientist's curiosity, it's a confounding variable for anyone planning to visit Titan. And that's not some far-off dream. NASA's Dragonfly mission is already in development, on track to arrive in the 2030s. Dragonfly will be a nuclear-powered drone, landing on Titan and hopping between sites to sample alien chemistry and perhaps sniff clues to life's universal recipe. Its mission planners are obsessed with one thing: the atmosphere. For Dragonfly to land safely, it'll need to navigate winds that sometimes whip 20 times faster than the surface rotates. The gyroscopic tilt could mean the difference between a pinpoint landing and disaster. The scale of Titan's atmosphere is mind-boggling. At ground level, the air is so thick you'd feel like you're scuba diving. Kelly Miller, a planetary scientist, put it simply: Titan's thick atmosphere, 1.5 times denser than Earth's, would make walking on its surface feel like scuba diving. And above those clouds are processes scientists barely understand. The James Webb Space Telescope recently spotted cloud convection tied to methane evaporation, another piece of the larger climate puzzle. Even the methyl radical, CH3, detected by Webb, is a molecule that could play a key role in methane's breakdown, hinting at chemical cycles distinct from anything we see on Earth. All of this suggests Titan's climate is not just slow-motion Earth, but a fundamentally different system. Its air moves as if it were a separate object, perched in space and stabilized by unknown physics. If a past collision or internal shift knocked the atmosphere off kilter, what lasting effect does that have on Titan's seasons, its weather, or the possibility of life below its crust? Because beneath those volatile clouds, another mystery lurks, a subsurface ocean, rich in ammonia and salts, perhaps as deep as 300 miles. Models suggest that only a few kilograms of biomass could exist in such a strange ocean, but the chemistry there might hint at possibilities for life as we've never imagined it. With every new mission, the list of questions grows. Titan's impact craters are unexpectedly shallow, suggesting its icy shell is warm and flexible, so features smooth out quickly, unlike on rocky planets. The surface is patched with hydrocarbon lakes, covering as much area as North America's Great Lakes. Cryovolcanoes may be remaking the landscape, spewing ammonia-laced ice from deep within. The sands are organic, the air is ripe with methane, and the chemistry is so rich that it could, in theory, support the building blocks of life. Though, as scientist Antonin Affolter cautions, Titan's uniquely rich organic inventory may not be as available for life as intuitively thought. Yet for all the data and debate, the core mystery remains. Why is the atmosphere spinning out of sync? What knocked it askew, and what keeps it locked in space instead of aligning to Titan's rotation or dancing to Saturn's pull? If this gyroscopic behavior is the key to Titan's climate, could similar patterns be hiding on other worlds, maybe even the early Earth? Dragonfly's planners are racing to solve those questions. They know that miscalculating the gyroscopic tilt's effect on winds could doom the mission. As Nick Teenby put it, the fixed tilt direction of Titan's atmosphere, uninfluenced by the Sun or Saturn, presents a new mystery. The engineering team is busy simulating descent scenarios, hoping that insights from Cassini-Huygens and the Webb telescope will let Dragonfly survive its perilous landing and deliver its treasure of data back to Earth. The implications stretch even further. If we can crack the code of Titan's atmosphere, we might not only bring home the first clear answers from an alien world, but also unlock new ways to understand climate systems, both here and across the cosmos. As Stephanie Milam at NASA notes, detecting the methyl radical allows us to see chemistry in action on Titan for the first time. There's a growing sense, even among seasoned scientists, that Titan is showing us a version of planetary evolution that could play out beyond our solar system. But here's where the stakes get even higher. The gyroscopic atmosphere represents more than an engineering challenge or a theoretical riddle. It's a ticking clock for the Dragonfly mission, and a warning flare for future explorers. If something as fundamental as the entire air mass can move out of sync with the ground, what else could be in store for robots, or someday humans, brave enough to touch down on Titan's surface? As the last bites from Cassini's archive yield yet another tantalizing clue, the Dragonfly team and the global scientific community are left with a critical question. Can we truly predict what waits for us in those thick, swirling clouds? Or will Titan's untamed atmosphere be the downfall of our most audacious exploration yet? The answer may decide not only the fate of a billion-dollar robotic insect, but the next chapter in humanity's search for life and our place in the universe. Picture this: a world where the sky itself spins with a steady beat, tilted eternally, unmoved by the massive presence of Saturn or the distant sun. Titan is not just strange, it's rewriting our cosmic playbook. As we look toward the next great leap in planetary exploration, the mysteries of Titan's gyroscopic atmosphere set the stage for both danger and discovery. What's at stake? For the Dragonfly mission, everything. Unlike the Mars rovers that crawl across rock and dust, Dragonfly is a drone, a rotorcraft designed to buzz through Titan's dense alien air. Its success depends on how well we understand that very air, which now reveals itself to be far more dynamic and unpredictable than anyone dreamed. Dragonfly will descend through Titan's upper clouds, encountering winds that swirl and shift, their patterns possibly linked more to invisible seasonal cycles than to anything we can model from afar. The atmosphere's stable yet mysterious tilt means that winds at altitude could veer sharply in unexpected directions, posing a direct threat to landing accuracy. As Lucy Wright puts it, Dragonfly's engineers must now plan for an atmosphere that seems to have a mind of its own. Yet, within this risk lies the thrill of potential insight. If scientists can solve the puzzle of Titan's gyroscopic air, they will not only secure Dragonfly's touchdown, but also unlock clues to atmospheric physics on a grand scale. Because, make no mistake, this isn't just Titan's secret, it's a new wrinkle in how atmospheres across the cosmos might work. Imagine future planetary missions, whether to exoplanets orbiting distant stars or to the hazy moons farther out in our own solar system. Each world may harbor its own rules, forged in ancient cataclysms or slow, hidden processes. Are there other gyroscopic atmospheres lurking in the darkness, waiting to catch explorers off guard? Every answer about Titan raises new questions for worlds yet unvisited. But let's zoom back in. Titan's context is unique. Its surface is sculpted by winds that race above hydrocarbon dunes the size of countries. Its rivers and lakes pulse with methane and ethane, while below, perhaps 300 miles down, a salty ocean sloshes unseen. The atmosphere is so thick and buoyant that, on Titan, you could literally strap wings to your arms and fly. And now we know that whole atmosphere wobbles and leans, like a cosmic topset spinning by forces unknown. This isn't just exotic trivia. The mystery of Titan's tilt has ripple effects throughout planetary science. Professor Nick Teenby says it best. The fixed tilt direction defies expectation. It suggests a past event, maybe a giant collision or a slow internal shift, set the atmosphere into this gyroscopic state, and nothing since has been enough to stop or change it. So, what could have caused it? Some researchers suspect an immense impact, similar to the one that formed Earth's moon, might have jarred Titan or its core. Others point to gradual processes, tides from Saturn perhaps, or interior heat-bending layers of ice. Yet Cassini's data rules out easy answers. The Sun, Saturn, and even Titan's seasonal changes only nudge the wobble, they don't drive it. This leaves scientists with a tantalizing paradox. The atmosphere is both stable and in motion, as if self-correcting, maintaining a gyroscopic balance with almost eerie persistence. It's as if Titan is guarding its secret, daring us to land, measure, and decode. Looking ahead, Dragonfly's descent will be the ultimate test. Engineers are already updating their models, factoring in not just regular winds but the newfound tilt and possible shifts in air mass. Predicting where the rotorcraft will touch down is now as much an art as a science, requiring real-time atmospheric sensing and last-minute course corrections. If Dragonfly succeeds, it will not just be a technical triumph, but a scientific one. With every flight, it can sample air currents, chart temperature gradients, and send back a torrent of data. It could catch the moment of a methane storm or chase the subtle changes that mark the shift of seasons. We'll move from models and guesses to direct observation. But imagine the consequences if we fail to understand Titan's atmosphere. A miscalculated descent could see Dragonfly blown off course, crashing into dunes or lost beneath clouds. An unforeseen wind could mean losing years, if not decades, of careful planning. That's the razor's edge of exploration. Ingenious science pitted against the unknown. Yet, in this pursuit, there are lessons for all of us. Not just planetary scientists and mission planners, but anyone fascinated by the nature of worlds beyond our own. First, Titan reminds us that even seemingly well-understood systems can harbor profound surprises. For decades, scientists assumed Titan's atmosphere would behave much like Earth's, or even that of Mars, driven by solar heating, planetary rotation, and tidal influences. But Titan's unique properties, its thick, nitrogen-rich air, the presence of methane, and its slow, stately seasons, shatter those assumptions. What does this mean for us? It means humility before nature's complexity. Even here on Earth, our weather systems and climate are governed by countless interacting factors, many only partially understood. Titan's mystery is a cosmic echo, reminding us that the universe is vastly more creative and more strange than our models can predict. Second, Titan offers a unique laboratory for the study of prebiotic chemistry. Its thick orange haze is laced with organic molecules, nitriles, methane byproducts, and more. The recent detection of the methyl radical, CH3, by the James Webb Space Telescope, as Stephanie Milam at NASA notes, lets us see chemistry in action on Titan for the first time. Here, the question isn't just whether there could be life, but what kinds of strange molecules might be synthesized under such alien conditions. For those of us watching from Earth, this is more than science fiction. The processes on Titan may shed light on our own origins, how life's building blocks first formed beneath a young, turbulent sky. If life can arise, or nearly arise, in a place so hostile and cold, what does that say about life's tenacity throughout the universe? Third, there are practical lessons for atmospheric science. Titan's wobble suggests new mechanisms for atmospheric stability, gyroscopic processes that might also occur in subtler ways on our planet. As Lauren Schurmeyer observes, lessons from Titan can provide important insights into processes happening on Earth regarding methane release. Understanding Titan's atmospheric motions could help us predict or even manage large-scale gas dynamics here at home, where methane is a powerful greenhouse gas and a key player in climate change. Beyond Titan, these lessons ripple outward. Every time we discover an exception, a world that breaks the rules, it sharpens our tools and widens our minds. The next time we see a hazy exoplanet from afar, hints of a gyroscopic tilt or erratic winds could warn us, expect the unexpected, prepare for the unknown. And so, Titan's wobbling atmosphere is a reminder, one writ in orange clouds and icy rivers, that the cosmos is a place of endless invention. Each new discovery breaks the chains of previous knowledge and invites us to imagine more daringly. Let's return, finally, to our guiding question. What is causing Titan's atmosphere to tilt and stabilize in such a mystifying way? The answer, as of now, is this. We don't know for certain. The evidence hints at a violent, ancient event or a complex internal mechanism, perhaps a blend of both. But in this mystery lies the heart of scientific adventure. As Connor Nixon says, Cassini's archive continues to yield remarkable discoveries. Titan is proof that the universe rewards patience, curiosity, and boldness. And here's a secret fact. Despite its strangeness, Titan's atmosphere is so dense and its gravity so low that if you were to visit, you could put on a wetsuit, strap on a pair of artificial wings, and take flight under your own power. Just imagine soaring over methane lakes, beneath the perpetual twilight of Saturn's distant light, all while the air around you dances to an invisible gyroscopic rhythm. This is the world we'll soon explore. The Dragonfly mission is set to write the next chapter, and every data point it returns will bring us closer to the answer, and to understanding the possibilities that await on worlds far from home. If you're as captivated by Titan as we are, make sure you subscribe, hit that bell, and share your own theories on what could be behind Titan's atmospheric secrets in the comments. What do you think knocked Titan's air off balance? And do you believe life could ever find a home beneath those orange clouds? Stay curious.